In today's video, we are talking about use of prior knowledge in machine learning. Recently, in machine learning, deep neural networks are being used mainly, and in the training of deep neural networks, only the data is used. Before deep neural networks, in machine learning, random forest and SVM and so on were used. At that time, feature extraction or feature learning was one of the things that one would do before you will put the data in the machine. That required prior knowledge in some sense. And till 1980s, in traditional AI, there was no learning of the machine. All knowledge was in some sense fed to the machine. So from then, when later on 90s and 2000, slowly more and more data was being used. And recently, in deep neural networks, only the data was used and no prior knowledge was used. However, now it has been found, despite a very large success of deep neural networks, that deep neural networks can also make use of prior knowledge. And today's talk about is how to use prior knowledge in learning of deep neural networks. First, let us discuss why and how prior knowledge can help in deep neural networks. First of all, if in training deep neural networks, there is sufficient data, then probably you don't need any prior knowledge, because with time, the deep neural network will learn the whatever information is needed for machine to take its uh, up to be able to apply it in the application that we want. However, that required data is increasingly becoming more and more, and therefore often we may not have enough data. In case of limited data, using prior knowledge can certainly improve the performance of the learned machine once the training is over. Second thing is, even when data is sufficient, sometimes what will happen is that learned machine may not obey the laws of the system that is supposed to be acting as. For example, if the machine is supposed, if you are using it in physics and to imitate the behavior of a physical system, then the input output of the learned machines should be satisfying the physical laws, and it may not happen with the amount of data you may have. And then using prior knowledge of the physical laws that the input output should satisfy the physical laws. If you include that, then that will be very useful for the trained machine, because that's how it should be behaving. It can also generalize, help in generalization and interpretation also. So once the machine has been trained and it is going to be used uh, in the field, then the generalization error that you are going to face can be reduced if you use prior knowledge. Again, if the data is limited. And also it has been found that prior knowledge can be used to improve the interpretability of the deep neural network. And interpretation of the decisions made by deep neural networks is becoming increasingly important, and especially in some particular applications. Now, what is the type of prior knowledge that we have been talking about? It can be the knowledge about the rules, about the domain rules. For example, if the system is supposed to behave like a physical system, then the system is supposed to satisfy the laws of physics for that particular system. Or if we are using the machine for modeling of some chemical systems, then it should be obeying the laws of chemistry, maybe chemical equations. So depending upon the application for which we are using the machine, uh, the for that application, the rules and the laws can be prior knowledge that we can use. The other is structural symmetry is properties. For example, symmetry, causality, and so on. The system may have to obey certain cause and effect relations, and the train system that you are going to get should then satisfy those cause effect relations, or the uh, result should be symmetric in certain kind, for example, in um, object recognition in the images. If the object in the image rotates, then it should still be classified as the same object. There may be in the application area certain constraints that some of the outputs or inputs have to satisfy, like monotonicity constraint. Some of the output should be positive and so on. So uh, the learned system has to make sure that those conditions are satisfied. So these can be made, these can be the prior knowledge that you can introduce in the machine so that eventually the learned machine will behave that way. So what are the different methods that can be used and have been used recently in how to integrate the prior knowledge in the learned machine? One is architectural priors. We are going to go through each one of them one by one in our discussion. So first is architectural priors. Deep neural networks has different architectures. So what is the architecture we should choose for a particular application? For example, we know that CNNs are good for object recognition and images, for speech recognition. RNN could be a good thing, and so on and so forth. The second is regularization based approaches. Now, the loss function that the machine during training is supposed to minimize, we can include in that loss function some other parameters which will enforce the some of the laws that are uh, machine uh, results supposed to obey. Another thing by which you can include the prior knowledges by doing data augmentation and generation. You can generate more data, which is in the direction of the way machine should be behaving. Then in the Bayesian methods, we will be discussing about the priors. In the priors, one can include the prior knowledge. Symbolic and statistical integration, we'll discuss about that. Also, physics-informed learning, when the system that the machine is supposed to mimic is a physical system, then it should obey the physical laws of that system. And as we talked about, the final result may need to satisfy some causal cause of effect relationships. Now, first, the architectural priors. How to include the prior knowledge in the deep neural network architecture. The examples, as we have already mentioned, we can, if we are using object recognition in images, we should choose CNN. And as we know that CNN has a particular kind of architecture, which was in fact designed to for the application of recognition objects in the images, and using that certainly improves the performance of the learned machine. RNN can be used for time series like speech recognition and so on. So for those applications, we should be using RNN. In certain kind of neural networks, we should be using graph neural networks. We have not discussed so far about the graph neural networks, but this is also an important kind of neural networks which we will be studying in the advanced part. So if, for example, the input to the network is a graph. Like if the application is social networks and so on, then the input may be a graph. And in CNN, the inputs will be two-dimensional or three-dimensional images. In RNN, it will be a vector. But if the input is a graph, then a different kind of architecture is needed, and that is graph neural networks. Choosing the appropriate architecture for the given application provides efficiency in learning as well as using less number of training data for the same performance, and it can lead to better generalization. Regularization-based priors, we know that in neural networks, deep neural networks, during training, we have to minimize the loss function. The loss function could be in terms of maybe norms. We can use L1, the most common norms are L1 norms and L2 norms. In the previous videos that we talked about, we emphasize more the L2 norms, but sometimes it is useful to use L1 norms because that encourages sparsity of connections in the learned network. And of course, there are monotonicity constraint and penalty functions that we can introduce to satisfy certain kind of behavior. In general, the loss function that we can choose is L, that we want to minimize in the training. It has two parts. L data, that is just the um, mean square error, or L1 norm or L2 norm of yi, and the output of the network difference of that we want to minimize. And then lambda is a positive constant you will choose, and L prior is an additional loss function that you attach depending on the kind of prior knowledge you want to introduce. For example, in physics-based regularizer, the system may behave as a differential equation. So, for example, if the system satisfies a second order differential equation, and for the input x to the machine, the output is fx, the fx output should satisfy as the second derivative with respect to the input x of some quantity. So in that case, to ensure that the learned system does behave approximately as the second order derivative, we can take the difference of the second order derivative from the fx and take L2 norm or L1 norm and take that as L prior and include here. Of course, when we take the overall loss function, we take it as the average over all xi, yi training sequence that we have. So here we'll have xi's, and there may be yi's here, and this is how the summation over them is included into this. You can include prior knowledge, but augmentation and synthetic data. So let's take the example of object recognition in images. Now, if in an image there is a chair could be in any orientation. You can rotate it by any number of angles, or you can even flip it around top to bottom and so on. Whatever way you take the picture of the chair in the image, the output should show that there is a chair in the image. So how do you make sure of that? You may have in the training sequence data xi, yi, xi is the image, y are the objects in that. From that initial data, we can create additional data. That is what we call data augmentation. So how do you do that? You take the picture of a chair in the image, and then you can rotate it. And three-dimensional rotations, there is software available to do that, and take another picture and then rotate further, take another, or flip around and whatever way you want to do it, and get additional pictures of the object from a single picture and add that to the training sequence. This way we can increase the data of each object from different rotations and flippings, even if, so that way, if you use all of that in the training sequence to train the machine, it will ensure that the result that you will obtain will be more robust about rotations and so on. And this has become a standard trick. And of course, this is one way to include um, invariance to the rotations and so on. You can, so this is the general thing we are talking about. If X is one data point, training data point, with, let's say, xi, yi is there, you put xi here. And if you want the trained machine to be invariant to some transformation t, rotations in this case, or some other transformation, you use that transformation on each xi to get a different image or training set xi tilde. But the label corresponding to yi will still stay there. So xi yi will include now txi yi as well. So this way you can augment the data and make your machine robust towards these invariances. The other thing we can use is to generate synthetic data. In this case, suppose you have a physical object that you want your trained machine to behave as. In that case, if it is possible to generate, in addition to the existing training sequence, to also simulate that physical object and generate extra simulated data from that. So this is called synthetic data because this is not the original data coming from the field available to you, but you, via simulation, you have generated more data. And this is, in fact, has become a very popular method in many of the things like communication, engineering, and so on, where it is so easy to simulate. And you add that simulated data into the training sequence. So this is how you can include the prior knowledge via data augmentation and synthetic data. Bayesian methods, if we are using, let's say, Bayesian neural networks. In Bayesian neural networks, if theta is the weights, set of weights, and D is the training sequence, the Bayesian method or Bayes formula says probability of theta given D is equal to probability of D given theta into prior distribution on the thetas, p theta divided by pd. So this is the thing. Now, if you are using Bayesian neural networks, the initial prior distributions on weights, p theta, we can start in such a way so that it emphasizes certain kind of data based on the prior knowledge that we have. So this way in Bayesian networks, by changing the prior distributions for the weight matrix, we can introduce the prior knowledge. Now, this is an important method, symbolic statistical integration. Deep neural networks, or the machine learning methods that we have been using, which have been using data to learn the machine, is mostly a statistical learning. But till 1980s, traditionally in AI, symbolic methods were used, in which instead of manipulating the data in terms of like real data or complex data, machines were manipulating symbols, and logical rules and other things were being used. So in symbolic AI, there is a symbolic representation of the data and it operates on the logical rules. This is how traditional AI was being used. Now, what is being thought is that those methods can be brought back and combine with the machine learning methods to improve the overall performance of the system. And this is one way of introduce prior knowledge in the learning of the machine. So what is the logical rules are kind? So this is one example of logical rules. If AX is some statement, A is some statement, X is some variable. So AX would mean that whether this statement satisfies is satisfied for given variable x. So ax takes value 0 or 1. Similarly, bx takes value 0 and 1. So what this says is if ax and bx are true, so that means if ax as well as bx both are true, then cx will be true. So this is one typical example in logical rules. Now, how we will enforce this kind of logical rules in the training of the neural networks is this rule we can introduce in as a loss function. We call it like L of logic, right? So earlier we mentioned that by introducing the loss function, some constraints, we can in a way try to make sure that learned machines more or less satisfies this. So to introduce this, to make sure that learned machine will satisfy this, we can put this as a loss function over all x variables. If ax is 1, bx is 1, then we want cx should be 1. So if ax is 1, bx is 1, then this quantity a1 plus 1. So if cx is 1, so this quantity will become 1 plus 1 minus 1 minus equal to 0. Max of this will be 0. So then the loss function will be equal to 0, which is what we want it to happen. But if ax is 1 and bx is 1 and the machine is giving cx to be equal to 0, then this will be 1 plus 1 minus 0 minus 1. This quantity will become 1 and maximum that will be 0. So by choosing this kind of loss function, we are trying to make sure that so the maximum of this will be actually in that case equal to 1, and we are trying to minimize that kind of weights which will tell that 1 here and 1 here, but this is 0, so that will be minimized. So our weights in the neural networks will be minimized for such combinations. So this is how we can try to make sure that the neural network will have weights which will try to satisfy this kind of rules. So this is used in application like natural language processing and knowledge graph completion and so on. Other methods, we are giving more details about including logic rules in neural networks because this is where a very active area where the traditional AI methods and the machine learning, deep learning methods are being combined to obtain better systems. In one method, which is called rule knowledge distillation, we consider two neural networks. One is teacher network, the other is student network. We construct teacher network, and at the output, we include the logic rule to make sure that the output satisfies that logic. So you take the neural network, take its output, and at the output, we make sure that we make the changes to the output to ensure that it satisfies the logical rules that we have been talking about. And then the corresponding changed input output, so corresponding by each xi, output will be yi after this modification. We create another sequence xi yi training sequence, which we feed to the student network. Student network is just neural network. And with this change xi yi, you come here and try to get neural networks which will try to match this modified xi yi. And then you get the new xi, yi's, feed it back here, and again run it, and you iteratively go through it. So via this, it allows data, that the initial training data that you have, and the logical rules together to make a student network that will satisfy roughly the logical rules, and it will therefore hopefully improve the generalization as well as interpretability as well, because this input output relationship now satisfy these logical rules also. This helps in interpretation. In the second method, neural knowledge rule layers, the logical rules that we want the network to satisfy, these are encoded as differential layers within the network. So you have the neural network. Within the network, at different layers, maybe hidden layers, you will encode this logical rule to make sure that this is satisfied as the data goes forward. And using that, ensuring that you train the neural network. So that way, finally, what you will get is a trained neural networks, which will try to satisfy those rules. The third method is somewhat similar. Here, again, in the neural network, we initially implement logical operation and or not as part of the network. We have studied in our earlier videos that all these operations can be implemented by a neural network. So implement these as modules inside the neural network, and then use them as part of the network architecture as we are training it to adapt to the different logical expressions that you will get. At the end of it, at the end of the training, you can run through a logical regularization mechanism, which ensures that something silly or unnecessary is not happening. For example, you may see after the training that there is a double negation is going on. So you can just remove that. So that makes the system more efficient. And similarly, some other things, if some logical rules are not getting satisfied, you may want to change that as well. There is one more method. This is to generate hybrid symbolic neural systems. And we explain it by an example of autonomous vehicles. We want to design an autonomous vehicle which is going to move around by itself on the roads. In going from the road, it has to go from a source to a destination location, and it will have to go through the roads where other traffic will be there. There will be red lights and so on. So it has to satisfy the traffic rules. It has to satisfy the safety rules that if there is a person in front of you, you have to stop and so on. So the way it can be designed in the hybrid case is the neural network part will process the sensory data. So there will be sensory, for example, there will be cameras and so on, which will be in the vehicle, which will be looking at the road to notice if there are objects and so on. So, and similarly, there will be other sensory data. So the neural network processes that. And at the same time, there is a symbolic logic you separately can enforce, which will enforce the traffic laws and the safety rules. So it will see that if there is a red light in front of it, it will just stop the car, irrespective of what the neural network is doing. Similarly, if it sees some person or another vehicle very close to it in front of it, it will stop the car. So this way, symbolic logic makes sure that certain rules are satisfied while the neural network is doing the other activity. So this enables explainable, again, such results are more explainable and accountable, because it will make sure that the traffic laws are being followed and the safety rules are also being followed in the decision making. Physics-informed neural networks. Now here we talk about a neural network which is trying to mimic a physical system, and therefore the resulting final system that you are going to obtain should follow the laws of physics corresponding to that object. So in this case, what we are going to do is, as mentioned earlier, we will try to implement the physical laws by including those in the loss network, loss function. So how we do that is we take the total loss function L that we want to minimize in the training of the neural network. It will have three components. One is the data loss, D data. So it measures the error between the network's predicted outputs and the available observed data in the training sequence, right? This is the basic loss function that we always have. Then in addition to that, there can be two other components of it. One is this makes sure that physics laws will be obtained. So if X and Y, the input X and the Y, are not following the physics law, there is a penalty to be given. So physics laws will often be as differential equations, and we gave in the beginning an example of the differential equations. So any violation of this will be penalized by this function. Then in addition to that, the physical object may have to satisfy some boundary conditions or some initial conditions, and that these are going to be satisfied by the trained machines will be ensured by the loss function L counts this. So the combined loss function is L is equal to L data plus lambda 1 L physics plus lambda 2 L conditions, where lambda 1 and lambda 2 are weighting factors balancing the terms. And these are going to be non-negative terms. So if lambda 1 is large, then this will be more emphasized in the trained machine and so on. Now, how these loss functions will be given. So the loss function corresponding to the law, the physical law. So physical laws are generally expressed as partial differential equations or ODEs. For example, Newton's laws, like dVt by dt is equal to ma kind of thing. M or ma is equal to f. So Newton's laws, and so this a is equal to b, the law written in that form can be written as a minus b is equal to 0. So then it becomes, you can write it as nuxt is equal to 0, where x is the position and or the state of the system at time t. So if this is ensured, that will imply that the physical law is being implemented. Now, if the neural network at any given time has the weight vectors theta, then the state or the output u theta x at time t, we take that and implement this differential operator on that. So n u theta xt. Ideally, this should set be equal to 0, but it may not be for at any given theta. And whatever its value is, we call it as residual rxt. Output at time t is x, corresponding to the theta parameters. So what we would like to ensure is that this loss function L physics is 1 by nr sigma I is equal to 1 to nr mod of r xi ti square. So take the residual, take their square, take the average over the all training data, and this is what we will try to minimize for this component. If you want to enforce some boundary conditions and initial conditions also, there, for example, at initial time t0, if the output is x, it should satisfy z0x. So output should satisfy 0x at the initial conditions. And if we are starting with theta, its value u theta xt0 should be equal to this. Similarly, at some other time t, some later time, at some points or some outputs xb, we want to ensure that the output is equal to GBXBT. So we want to train the machine that these initial conditions and these boundary conditions are satisfied. To ensure that, we use the penalty function or the loss function. C cons is equal to 1 by MB. So you take the value, actual value at time Tj, this xbj is having, and the difference of that from what it should be, take mod square, add up all possible these points, xpj and tj. Similarly, you find this difference of the what initial condition should be and what it is for a given theta, take their square of the average, and you add that, go back to overall loss given here, and you use this loss to minimize via the training sequence. So this is how we can ensure the physics laws and the boundary conditions for this case. Now, whatever these methods we have talked about, trying to implement some conditions via loss function, these are called soft constraints. Why these are called soft constraint is because by including them as penalty functions in the loss function as here, what we are trying to ensure is that the system will satisfy these conditions. But it may not be satisfying for all of these points, the initial conditions and the boundary conditions, or even the physical laws. We are just trying to make sure that we are encouraging system, the final system, to be as close to satisfying the condition as possible. So these are called soft constraints. Sometimes this is not enough. Because in case of, for example, if there are safety constraints, like autonomous vehicle, if it is walking, and there is a red light in front of it. So it's not enough that it should approximately satisfy the point that it will stop, or most of the time it will stop. We may want to make sure it will always stop. So these are hard constraints. So a system, trained system that we are going to have, we want to make sure that it will certainly satisfy some constraints. In that case, for those particular conditions, we can do something more. We take the output of the system for any weight functions, and there at the output we put a differential projection layer. What it does is it takes the neural network output and then make sure that the output will satisfy the constraints strictly. For example, we can make sure that the output will satisfy some convexity constraint or affine constraints. So we put a projection on the output to satisfy these things. This will ensure the final output you will get is satisfying those hard constraints. Finally, we talk about using causal inference kind of prior knowledge. We may want to ensure that the trained system satisfies some cause-effect relationships. Now, how it can be done is, beforehand, you have this knowledge about the system that certain causes will produce certain effects for that system. And we want to make sure that the trained system does satisfy this. So a priori, what you do is all those causal relationships, cause effect relationships that you want to ensure, you reflect them and make a directed acyclic graph based on them. And that graph can be then included into making a graphical neural network. And starting with that graphical neural network, you train it based on the data to minimize loss. So what it will ensure is that the cause-effect relations that you included here will be there in the final neural network as well. So these are some of the different methods people have been recently discussing to incorporate prior knowledge in the system. As we said, that it can make the system more efficient, it can provide better generalization errors, and it can make sure that some safety rules and other things can be implemented. There are certainly open questions because this is a very new and important topic in AI machine learning. One is how to automatically extract prior knowledge. So this prior knowledge could have been given by human beings, experts, and other things. But what we may want to do is how to actually maybe extract that itself from the data. Second thing is balancing data and priors. Remember in the loss function, you have the L loss corresponding to the original loss function, and then lambda, and then losses corresponding to the physical loss and so on. That lambda gives the balance between the importance you want to put in the data part and in the prior knowledge. If lambda is large, then you are giving more importance to the priors. So what may happen is the result that you will get, the trained system, may be overfitting to the priors. And that itself may not be very good because priors may not be perfect. If the lambda is too small, then you are giving a lot more importance to the data. And if, in fact, if it is zero, then you are not using any prior knowledge on it. So we should choose lambda appropriately so that the data part and the prior part are having balancing effect in the final machine that we get. We have talked about the different kind of priors, symbolic priors, statistical priors, physical priors. Now, how to incorporate symbolic and physical priors, physical laws in the trained machine. So this is still a topic of interest today. We did talk about interpretability of the final trained machine, and interpretation or explainability is very important today. Now, if you make this final system very much interpretable, for example, you could simply use the symbolic AI. If you use only symbolic AI and no data, that the results can be very nicely explained. But we have seen that this is not enough, and this may lead to very restrictive kind of systems, and the model may become very restrictive. So there is a trade-off between interpretability and the model flexibility. If you just take deep neural network, no priors, then of course we know that it's very difficult to explain that final system. So we need to consider a balance between interpretation as well as the flexibility of the models. Finally, the conclusion is prior knowledge is essential for robust, generalizable, and interpretable models. Many frameworks exist, as we have given briefly in this talk. We have to choose one of them. Some of them may be more useful than the other for the application we have and the kind of system we want to build. And we have to pick it properly and then train the system. Thank you very much.